Scientific Notation Part 2, Unit 2, Lesson 3. Please make sure you take notes as you watch the video on note sheet number 3. And if you've forgotten your note sheet at school, don't forget it's posted on Blackboard. So we're going to be talking about comparing numbers in scientific notation. In yesterday's lesson, we learned that scientific notation is a mathematical or a scientific way of comparing either very big or very small numbers in a shorter way. And in today's lesson, we're going to learn how to compare scientific notation by using order of magnitude. Order of magnitude is just a big fancy way of saying that you are trying to figure out which is bigger or smaller, and you're going to do that by looking at the exponents, and if the exponents are the same, you are then going to defer to the factors. We're going to talk a lot about that more later, but first, let's get an introduction from Math Antics.
Being able to quickly identify a number's order of magnitude is pretty handy. For example, if the order of magnitude is a big positive exponent, then you know right away that you're dealing with a really big number. But if it's a big negative exponent, then you know you're dealing with a really small number. And if you're comparing two really big numbers like these two, or two really small numbers like these two, it's hard to tell at a glance which is actually bigger or smaller. But if you see them in scientific notation, it's easy to see that this number's order of magnitude is bigger than the others, which means that it's bigger. And this number's order of magnitude is less than the others, which means that it's smaller.
So clearly, you can see that order of magnitude is going to be very easy when you're looking at the exponent. First of all, we're going to talk about positive and negative exponents. So we learned yesterday that a positive exponent means that a number is very large, while a negative exponent means that it is very small. The one thing I want you to remember, though, and it's really important, is that a negative exponent does not mean the number is negative. It merely means that that number is very small and is probably getting really close to zero, but is not going over zero into negative numbers. It just means that it is very, very small. So in example 1, what we're going to do is we are going to compare each set of scientific notations, and we're going to complete with either a greater than, less than, or equal to. So in example number 1, the top row, we're looking at 3.1 times 10 to the third power, and we are comparing that to 3.1 times 10 to the fourth power. Well, knowing what we know about positive exponents, we know that we are going to be moving our decimal one more space to the right with 10 to the fourth power. So that number is actually going to be larger. Now, you're not going to need to do this, but by way of illustration, I'm going to show you if we actually wrote out those numbers, you can clearly see. So 3.1 times 10 to the third power actually looks like 3,100 in standard form. And 3.1 times 10 to the fourth power in standard form is 31,000, a much larger number. Now we're going to look at the negative exponents. 3.1 times 10 to the negative third power and 3.1 times 10 to the negative fourth power. I want you to remember that when we are looking at negative exponents, that means we are moving that decimal spaces to the left. So if you are moving your decimal less spaces to the left, you're shifting it less spaces to the left, that means the number is going to be larger. And therefore, 3.1 times 10 to the negative third power is greater than 3.1 times 10 to the negative fourth power. So again, for illustration purposes, I have gone ahead and written these numbers out for you so you can see the difference. 3.1 times 10 to the negative third power in standard form is 0.0031, while 3.1 times 10 to the negative fourth power is 0.00031, which is a much smaller number. Now, sometimes when I'm confused about where numbers fall, meaning larger or smaller, I find it very helpful to have a number line. So on this number line, I have clearly marked 0 with a red arrow. And what we're going to do is we're going to plot the smaller number first. So 3.1 times 10 to the negative 4th power, which goes almost to 0. It's almost there, but it is not at 0, and it is certainly not past 0. Now, when we're trying to plot 0.0031 or 3.1 times 10 to the negative 3rd power, you can see that it is slightly larger, slightly closer to 0.1, which makes it, of course, larger on the number line. All right, it's time for you to give it a try. I would like you to please pause the video and work examples 2 and 3 on your note sheet, keeping in mind that you're going to look at those exponents first. Pause the video, restart it when you're ready to check your work. Okay, how'd you do? Let's see here. We've got 7.4 times 10 to the 7th power, and we've got 7.4 times 10 to the 10th power. Clearly, 10 to the 10th power is going to make 7.4 larger, so the greater than sign is going to go there. Or it's going to read 7.4 times 10 to the 7th power is less than 7.4 times 10 to the 10th power. Now in example 3, we're looking at negative exponents. We've got 7.4 times 10 to the negative 15th power, and we're comparing it to 7.4 times 10 to the negative 12th power. Again, we're shifting that decimal to the left, and with 10 to the negative 12th power, we are shifting it 3 less spaces to the left, which would then make 7.4 times 10 to the negative 15th power less than 7.4 times 10 to the negative 12th power. If you are confused, please pause the video and just go ahead and write out the numbers and you'll see. All right, now we're looking at example 4. In example 4, this example is very different from what we've been looking at previously. So what you can see when you're looking at these examples are, these exponents are the same. So if you come into a situation that you're comparing and the exponents are the same, you are then going to defer to the factors. Well, let's see here. The factor in our first scientific notation set is 2.5. Our other factor is 4.7. So knowing that we're going to be shifting that decimal to the right 5 spaces on both, we can safely say that 4.7 times 10 to the 5th power is greater than 2.5 times 10 to the 5th power. Now, we have the same situation going on with our negative exponents. We have 10 to the negative 8th exponent on both sides. So, what are we going to do? Well, we are going to again defer to our factors. Clearly, 5.6 is larger than 3.3. So, 5.6 times 10 to the negative 8th power is greater than 3.3 times 10 to the negative 8th power. Now it's time for you to give it a try. Please pause the video and work examples 5 and 6 on your note sheet. Restart the video when you're ready to check your work. Okay, so how'd you do? In example 5, we can see that we have 10 to the negative 7th power on both sides. So we are going to defer to those factors, and we can see that 3.4 is greater than, we know that, 1.61. Again, we're moving that decimal to the right 7 spaces on both sides. So we know that 3.4 times 10 to the 7th power is greater than 1.61 times 10 to the 7th power. In example 6, we have the same thing. We have 10 to the negative 5th power on both sides. So again, we are going to defer to the factors. Here we know that 3.4 is greater than 1.61. On both sides, we are going to be shifting that decimal to the left 5 spaces, which then makes sense to have 3.4 times 10 to the negative 5th greater than 1.61 times 10 to the negative 5th power. All right, in examples 7 and 8, we are looking at problems that have both different different exponents and different factors. So in example 7, we can clearly see that we've got 9.75 times 10 to the 5th power. On the other side, we've got 8.2 times 10 to the 10th power. Don't be fooled. Don't look at the factors. Here, 9.75, yes, it's bigger than 8.2, but you are going to always look at those exponents first. So 9.75 times 10 to the 5th power is less than 8.2 times 10 to the 10th power. In example 8, we've got 6.98 times 10 to the negative 8th power as compared to 2.45 times 10 to the negative 2nd power. Again, don't be fooled. The factor 6.98 is bigger than the factor 2.45, but we're not going to be fooled by that. We are only going to look at the exponent. And because the exponent is only going to move to the left 2 spaces with 10 to the negative 2nd power, we can say that 6.98 times 10 to the negative 8th power is less than 2.45 times 10 to the negative 2nd power. All right, it's time for you to give it a try. Please work examples 9 and 10 on your note sheet. Pause the video and restart it when you're ready to check your work. All right, I hope you did well. Let's see here, we've got 4.256 times 10 to the 7th power, and we are comparing it to 1.07 times 10 to the 8th power. We again are not going to be fooled by those factors, and we clearly can say that 4.256 times 10 to the 7th power is less than 1.07 times 10 to the 8th power. Now, in example 10, we've got 7.83 times 10 to the negative 2nd power, and we are comparing it to 9.25 times 10 to the negative 7th power. Don't be fooled. Yes, you can easily say that 7.83 times 10 to the negative 2nd power is greater than 9.25 times 10 to the negative 7th power. Make sure you write down your questions and come to class ready to ask them if you're confused by any of this. In the meantime, that's it for today. Please put your note sheet in your binder so you have it with you in class tomorrow, and I hope you have a great afternoon.